Hello, everyone, and welcome to the second session of aircraft design here at the forum. This will be our final aircraft design session. We're looking forward to a very full day of quite a now to the last two presentations of aircraft design session two. Um, and we're pleased this year to again be able to showcase the student design winners from this 37th annual student design competition, which was sponsored by Leonardo. And of course, this competition was looking at relooking at the aerial screw 500 years later. First, we're going to hear from our undergraduate winner, which is from the Delft University of Technology. Representing Delft are two speakers. One, Mr. Nick Pauly, is a master's student in control and optimization at Delft. Uh, this student competition was actually his first introduction to the Vertical Flight Society, and he participated in it at the end of his bachelor's degree program. Also, Mr. Sungi Han is a Master's of Science Aerospace Engineering student at Delft now in the Aerospace Structures and Materials program, and he's currently working on large-scale additive manufacturing and robotics. So we're excited to hear more about their student design competition paper or project. Take it away, gentlemen.
All right, thank you very much. So, hello everyone. My name is Nick Pauly. Thank you for tuning into our presentation. I'm here with co-presenter Sungyan. So, as Jeff already said, we are from the Delft University of Technology, from the Netherlands, of course. And so we are the winners of the 2019 VFS Student Design Competition, the undergraduate one, for Leonardo's Aerial Screw. And so in this presentation, we're going to show you the design that we made for our concepts. So here's how we're going to go through it. We'll start by introducing the student design competition and the general requirements. And then we're going to talk more about the concept exploration and how we ended up with our design and introduce the Solidity one. So Sungi will then explain how we calculated and designed the aerial screw rotors. And after that, I'll go over the general performance and have some time for questions. So to give a bit of context, every year the VFS holds a student design competition and they publish a request for proposal with a different theme or topic each year. So in 2019, the 37th design competition was in honor of the 500th anniversary of Leonardo da Vinci's passing. And among his other famous works, Da Vinci also sketched out one of the earliest concepts for the manned VTOL. Drawn in the late 15th century, the aerial screw consists of a rotor consisting of a single corkscrewing linen and wooden blade, which was then to be powered by a team of people. But to see how feasible it would be, the VFS and Leonardo helicopters called for VTOL concept designs based on this sketch. So in the winter of 2019, we took on this project as our bachelor graduation project, and we worked on this for 10 weeks full time. Now, so what does aerial screws place in aerial flight history? Modern rotors, they actually came from ship propellers. So from applying Archimedes screw as a propulsion after steam power became available, which in then became bladed propellers, which was applied to aircraft and after that helicopters. So 4 centuries earlier, Da Vinci reasoned that if a screw could push water, a screw could also propel itself by pushing air, but of course in his time he didn't have enough power or the material strong or light enough for this design to be feasible. Um, but of course, in this day, technology was too limited for it to be viable, so it was left in the wayside. And the point of this project was to investigate whether his rotor design could actually work with modern technology. Um, so I mean, to go back on the proposal requirements, they were as follows. We had to design an experimental demonstrator VTOL craft capable of carrying a single pilot weighing at least 60 kilograms. And the Vinci's aero screw inspired rotors were required. These were defined as a single bladed rotor, with that blade having a solidity equal to or greater than 1. And to demonstrate this in an animation, the flight mission requirements were extremely low. Like we just needed to take off, hover for 5 seconds, travel for 20 meters in 1 minute, and then hover again for 5 seconds and land. Uh, so before we actually started looking at the requirements, a concept orientation was performed to look at all the possibilities, such as the conventional craft, a quadcopter design. We also added in like our own original IDs, like the nested coaxial, for example. And then we went on with our concept selection. So Having a complete overview of all the possible aerial screw configurations, the following concept selection process was followed. From the 18 configurations, a preliminary trade-off study was performed based on screw configurations, control options, propulsion systems, with the use of the book matrix analysis. And from this, we got to 3 screw configurations, 3 control options, and a final propulsion system. Before a more detailed trade-off was performed, we also had the possibility of a ducted screw that we looked on. And the detailed trade-off was performed on the basis of performance and the RFP requirements. They were eventually a final concept as the baseline for what becomes actually the Solidity 1. So, to talk about ducts, during the concept exploration, we found the Hiller flying platform. Some of you may know it before. This is like a coaxial ducted rotor platform, which is controlled by a pilot shifting his body weight. So basically like a Segway. And we also decided to adopt these ducted rotors because it provides a performance boost by reducing the tip losses. But they also contribute directly to generate lift by the Coanda effect. And it was found that those slips also provide a lot of stabilization, as can be seen in the video, which then, of course, improved safety. So in the Hiller platform, the stabilizing effect was so strong that they even had trouble going faster by CG shifting alone, which limits the forward speed. So with these configurations in mind, we found 3 potential designs. A nested coaxial that we talked about before, with rotor spinning in opposite directions, a tandem configuration, and a tilted configuration. And these 3 concepts won out because they were counter-rotating designs that were viable with aerial screws. So when we analyzed our 3 leading concepts against about a dozen criteria, in the end, the tandem design won out because it enabled higher speeds, which in turn gave us better range, which scores higher in the competition rules. Which then led us, of course, to our final design, Solidity 1. To give an introduction around the vehicle, it's a tandem electric VTOL capable of carrying a single pilot. And of course, we went for the electric propulsion, mainly because it's sustainable, it's compact, it's lightweight. So we have a motor mounted on each rotor shaft and a battery packs below the pilot. For the ergonomics, we had to test, of course, whether you had enough visibility, whether you could reach controls, whether you got, whether the seating was high enough, which is why we tested this in virtual reality so we could enter the vehicle. And of course, we checked if it was actually manufacturable. So we decided that the rotor and duct should be made from composite size to improve the stiffness, reduce the weight, and improve the manufacturability. The complex shape here, that can be made by machining a foam core and hand layup around it. But the duct lips, they are also cored with milled foam, whereas the duct walls, because they need even more stiffness, are made of a honeycomb core. So we went for a ducted design and reduction in tip losses as well for safety and stability. But of course, these very, very unique rotors that you can see over here, based on the Da Vinci's aerial screw. And we named our vehicle, of course, for its rotors with the blade solidity equal to 1. And when seen from above, there are no gaps in the rotor disc, meaning that it's solidity of 1. And these rotors have the benefit of being very compact and generate a low noise. Furthermore, we also had custom controls. Since the cyclic and collective is not really possible for this rotor design, we went for vanes underneath the rotor for roll and yaw. And then we adjusted the differential pitch, the differential RPM, so we could have a pitch control. But Sungi will now go more in detail about how we actually calculated those loads on the aerodynamic surface. So, Sungi.
Yes, thank you. So to design our vehicle, we needed a way to estimate the performance of our aerial screw in flight. We wanted to apply blade element theory because we really wanted to understand the mechanisms at play in the aerial screw. This is something that's encouraged by the TU Delft, but also is also the point of this project. Leonardo and the VFS wanted to explore the physics of the aerial screw. What's an advantage of blade element theory is that it's quite simple and yet it gives accurate results, and especially suitable for rapid design iterations because the results only take a few minutes to generate, and you can really see where it's going well and where it's going wrong and what you can adjust to improve it for the next iteration. Early on, we rejected CFD because of the shape of the aerial screw. As you can see on the outer edge, we have quite a long chord length. This gives us a Reynolds number of 30 million. This is on par with the Reynolds number of a airliner's wing. And as CFD costs scale with Reynolds number to the third power, we thought this is not the way to go for rapid design. So why do we pick blade element theory? What is blade element theory? For anyone who isn't familiar, in blade element theory, you divide your wing or rotor blade into several blade elements and you integrate along your blade element. For each element, you calculate the lift and drag as if it's going in a straight line, simple calculations in 2 dimensions, and you add them all to get your total rotor's thrust and power. However, for the aerial screw, it wasn't immediately obvious how you could do this. The complex shape doesn't lend towards straight cuts. However, we took some inspiration from marine propeller design. As we spoke about earlier, the marine propeller is sort of the middle cousin between modern rotors and the Archimedes screw. It has quite a high blade solidity, not quite as high as our aerial screw, but somewhere in between. And though it has multiple blades, they are still quite squat and they have a similar aspect ratio to us. So what they do in blade element theory, actually blade element theory comes from marine propellers. And what they do is they take round slices of their propeller blade, and then they unwrap these into flat segments, and then they do the same as we do for modern rotor blade element theory. They do simple lift and drag calculations, and then they integrate these to get your total thrust and drag. These slices look like this. They are semicircular arcs, and we apply the same principle to our aerial screw. Of course, since our aerial screw sweeps a full revolution from the leading to the trailing edge, we end up with essentially circular slices. And we unwrap these into a flat 2-dimensional case, and we just end up with a very long cord. And then we just do lift calculations, we do drag calculations, and we integrate along the rotor blade from the root to the tip to get the total thrust and drag and the power, sorry. So during exploration, we found that we actually have very little freedom in the shape of our airfoils along the blade. The pitch angle of the blades, of the airfoils, and the chord length along your radius are actually just mathematically related to the geometry of your overall helical shape of your aerial screw. Unlike a conventional rotor, we can't adjust for blade twist angle or chord length for optimal performance. We also don't have a collective or a cyclic mechanism. We don't have a swash plate. We can deform the aero screw during flight to account for different flight conditions. For us, the aero screw is just a fixed static design. This made it challenging to ensure a positive angle of attack during forward flight, for example. We ran a sensitivity analysis to optimize our rotor. What we found was that as you go towards a lower radius and a higher pitch, this means a narrow rotor and a taller rotor, you actually get better thrust efficiency. This is because the angle of attack is better when you have well, the only way to increase your blade pitch angle was to go for a narrower and taller rotor. This improves the angle of attack and improves your lift generation. And also going for a narrow rotor helps with screw mass. We 3D printed and tested these rotors with and without a duct. And we put them on a propeller test bed, and we did some calculations and verification of our calculations with actual prototype. And finally, we ended up in a screw shape like this. As you can see, the airfoil starts quite horizontal, parallel to the floor. And as you go towards the trailing edge, you end up with a steeper angle. We used camber like this because it was the only way we could control how much thrust we get and different flight conditions. We tune the camber along a radius in the same way you would adjust the chord and the blade pitch angle in a typical helicopter. Also, to help with flow reversal, we run at quite a high RPM. RPM in hover is about 1,500. So as you can see, we have quite a unique rotor here. We have, as you can see, the outer edge is longer than the inner near root. We have a longer chord length. This is essentially an inverse taper. And we have quite a squat rotor with an aspect ratio of 1.3. Now, the benefit of this rotor is that it is very quiet. We ran some preliminary calculations, and we thought that the rotor itself would only be about as loud as a loud conversation. This low noise is due to having a low tip speed. We are only at about 95.3 meters per second. And we have no blade vortex interaction since we only have a single blade. And also we have a duct around our rotor, which helps with noise isolation. One downside to having a single bladed rotor is that you have an oscillating center of lift. The center of lift is located somewhere in the middle of the chord between the leading and trailing edge. And as this rotor rotates, of course, the center of lift rotates, which gives some torsion in the central airframe, which should be addressed, as it could give fatigue failure. Having an inverse taper ratio and squat to aspect ratio means we have some extreme tip losses. In this figure from Leishman, you see a typical thrust distribution of a helicopter rotor. As you can see, the tip loss is really localized at the blade tip, and you lose about 10 to 15% of your total lift. However, for Solidity 1, it looks like this. The tip losses actually affect your entire rotor. We lose about 40% of our thrust. And this is why we ended up with a ducted design. Even though there was some discussion over whether we should do this, as the entire point of this project was to show off the aero screw, and putting on a duct under rotor hides the aero screw from view, but the performance gains were too significant to ignore. What we ended up doing was assuming that the duct would reduce the tip losses by half. So we didn't assume that the tip losses would be eliminated completely, but we just, as a conservative measure, we assumed a midpoint as a compromise. As for controlling the vehicle, we placed vanes under the rotors. These vanes can move together to roll in, to create a rolling moment, or they can roll, they can deflect asymmetrically to create a yawing moment. For pitch control, we use differential RPM. One rotor rotates faster than the other. This creates more thrust, and this creates a pitching moment. As we mentioned earlier, due to the Coanda effect, the duct clips create quite a bit of lift. About 25% of our total thrust comes from our duct clips. And when you have forward movement or a rotation, the relative movement of the duct relative to the air around you creates a imbalance in the air velocity around your ducts. This causes what we call a duct restoring moment. When you try to tilt or go forward or try to move the vehicle in any way, the duct clips will try to pitch you back and against the direction of movement. While this is, and in the case of stability, this is very nice. If your vehicle is moving in an unexpected direction, the duct clips will restore you back to horizontal. This is what we saw in the Hiller flying platform, and why it's so stable and easy to fly for a pilot who's just simply moving his CG around. Now, what this does mean is for forward flight, we need to maintain a pitching moment. The two rotors have to run at different RPMs to counter this duct restoring moment if you want to maintain forward speed. However, doing that also means that your two rotors will create different torques, which means you have to deflect, you have to correct for this by deflecting the vanes for yaw. To simulate this and check the vehicle stability, we made a 6-degree of freedom flight mechanics model. And to make it easier to fly, we also included a stability augmentation system with a PID controller to make Solidity 1 easier to fly for a pilot. As for the power plant, we investigated several different power sources. We looked at electric as well as several combustion engines. If you'll recall, the original VFS proposal asked for a 1-minute flight. So to just give us some breathing room, we initially sized for a 2-minute mission. And as you can see in the figure, at 2 minutes, electric propulsion is almost twice as mass efficient as a combustion engine. This is due to the low investment in mass due to the low motor mass. Once we were confident that we could fly, once we escaped the ground effect, we started to investigate what the battery pack capacity would do to our velocity and range. What we found was that as you increase your battery mass, your vehicle gets heavier and your velocity drops. But this only gets severe at about the 25 kilo range. At this point, the vehicle struggles to fly, and so we ended up going for a 25 kilogram battery pack, which gives us the optimal range. What this means is that we ended up getting an endurance of 5 minutes. And if you refer to the power graph earlier above, you'll see that at the 5 minute point, electric and two-stroke piston starts to cross over. And it's actually not clear whether we should have gone for electric. We might have had better results if we actually went for a combustion engine. Shown on the left here now is the power curves for a typical helicopter. As you can see, the induced power drops, and this means there is a dip in the total power required. And the helicopter flies most optimally at some forward velocity. This is due to the helicopter blades feathering out on the advancing side using a cyclic. This makes your lift vector more vertical, and you have less drag from it. However, for Solidity 1, this is not the case. We don't have a swash plate. We don't deform our rotor. Like the rotor is really designed for hover, and we don't benefit so much from forward flight. So although there is a slight reduction in induced power, just due to the velocity flattening out, there's no dip in the power required. This limits our top speed to about 14 meters per second. And as you can see, we theoretically could fly at an altitude of 830 meters. But however, due to having a 5 minute battery, you would actually only reach about 420 meters, and you will have to figure your own way back down. Now I will hand the word back to Nick, who will take us back to the competition requirements and see how we compare to comparable aircraft.
All right, thank you very much. Yeah. So what does this mean actually for the competition requirements? So with the design finally completed, the vehicle was verified against the competition requirements. And on the left here, you can see the mission requirements, and on the right are the values of our vehicle. I think it's best demonstrated by a short animation. For example, for range, the Solidity 1 actually reaches like 4.5 kilometers instead of the 20 meters. That's also why I sped it up a little bit so that it's quicker over. It also reaches a much higher altitude and much higher velocity. Now, since the competition requirements were so easily met, this slide shows the dimensions and performance of the vehicle compared to vehicles that Solidity 1 is based upon. The Piasecki Air Jeep looks very similar to ones, and it's designed to carry more passengers. It has a similar shape and comparable surface ceiling. Only the difference in speed is explained by the difference in power to weight ratio, which is over twice as high, because the vehicle is about 10 times as large. Because of our tandem design, we did improve on the Hiller platform talked about earlier, achieving a velocity twice as high. But it underperforms the Piasecki since it's on a much smaller scale. So that was our presentation. I'd like to thank you for your attention, and if you have any questions, then please don't hesitate to ask any.
Nick and Sungi, thank you for your presentation and your group. That was excellent presentation. We do have one question here from Emily Fissler, who asks, when using differential RPM for pitch, what is the response time for the aircraft? Is there an issue with the inertia?
Yes. So question is if there's a response time due to the differential in pitch. Yes, but it's very little. One of the reasons why we opted for an electric design is because when adding a change to RPM, it's almost immediately an RPM. So there's no delay there. The only delay is in your aerodynamic flow, which is only a few seconds. However, we accounted for this as well in the 6 degrees of freedom, and simulation. And since the vehicle is kind of inherently stable, this doesn't pose a problem. So does that answer your question? Or?
Well, we'll see if she responds more, but I think it sounds like you've gotten that. I have to admit some ignorance in the details of this competition rules. You mentioned you needed to have a solidity greater than 1. Were you constrained to having that be a single blade screw, or could you have had a multi-blade solidity 1 setup, like a stacked set of blades, for instance? Is that
The requirement proposal did ask for a single bladed rotor, since that's also what Da Vinci's design used.
Yeah, fair enough.
Also, for the previous question, I'd like to add that our rotor, because it's a foam core composite, it's quite light and quite responsive to changes in RPM from the motor.
Okay, another question here. Very nice design, first off. You mentioned some experimental tests of your aerial screw. Do the results compare well with your BET analysis?
Yes. So what we did with our tests is we tested 2 different rotor configurations, mainly to test the aerodynamic formulas. And the one result that we got from the tests is the interaction between having a duct and having no duct, since that's the thing that we were quite uncertain of, what the effect of a duct exactly means on the rotor calculations. And that indeed showed that the tip loss is around 49% or something. It was, or that it was indeed very much around the 50% that we originally estimated to.
Okay. Emily just said that you answered her question, but she had another one, wanted to know, she may have missed it. What was the total weight of the vehicle in the end?
I'm not sure if I can remember that correctly. It should be on the slides.
It's about 140 kilos gross, I believe.
It should be around that range, yeah. Yeah, the takeoff weight, including the pilot, is about 210 kilograms. So, yeah. So the empty weight would be around 140, 150 kilograms.
Okay.
Mm-hmm.
Give it a second here and see if any other questions pop up on the chat. Did you guys get to building any kind of scale model of it? I saw you had a lot of computer simulation. Did you ultimately get to the point where you built a little like RC model or something like that of your vehicle, or was that beyond the
That's still planned in the future. It's something I definitely do want to do because it would be quite cool to see this thing fly. But we haven't had a chance yet. We've been quite busy.
Mm-hmm. The main problem here lies that it's very difficult to find a controllable thing that controls this, since we could easily adapt like a drone configuration if we had 4 rotors, but because we have vanes, it's very difficult to implement this. So that's still a work in progress. Yeah.
Another question, actually. How did you guys go about sizing the vanes? I know historically, kind of these vane control systems have been somewhat pernicious and difficult to get sized.
It was actually fairly easy because we have quite a high downwash. We have a downwash since we have such a narrow rotor. To fly, we have a downwash of, I believe, 25 meters per second, gale strength winds. So we found that even with small rotors, you can, well, small vanes, you have pretty hard control.
Oh yeah, what disc loading are you at? That's a good question.
I don't know the number in the top of my head, so quite high. And it's 24%. It's similar, let's say, to the V22 Osprey. Those levels.
Okay. All right. Well, doesn't look like there's any more questions coming in. With that, we'll thank you again and wish you luck in your grad student studies. We'll pause just for a minute or two here so we can pick up at 12:30 the graduate student presentation. Thank you.
Thank you.
All right, and now we are here to our final presentation of aircraft design at the forum. We're pleased to hear from the University of Maryland. They were the graduate school winners for the aerial screw competition, the 37th student design competition. They're represented by two members of their team today. First is Mr. James Sutherland. James is a fourth-year PhD student and currently works in the Alfred Gesso Rotorcraft Center under the advisement of Dr. Anubhav Datta. His research is focused on fabricating, modeling, and testing advanced geometry rotor blades for the Maryland tilt rotor rig in the Glen L. Martin wind tunnel. In 2017, James graduated from Villanova University with a bachelor's degree in mechanical engineering and mathematics. Last year, James was indeed the team captain for the UMD graduate team. And for all of our industry partners who are out there online, James is looking forward to joining with one of you upon graduation, and he hopes to be the lead engineer in charge of rotor design for your respective company. Miss Katie Cromali is a graduate student as well at the University of Maryland and works under Dr. Roberto Celli in the Alfred Gesso Rotorcraft Center. Her research involves simulating rotorcraft interacting with water with the goal of enabling the design of new rotorcraft intended for amphibious operations. Before graduate school, Katie received her bachelor's degree in applied physics and computational mathematics from the Christopher Newport University. And in 2020, Katie was also part of the graduate team, which won first place. And I guess also won the best bonus task. I'm looking forward to finding out what that is. So take it away.
Yes, thank you, Jeff, for the introduction. And hello, everyone. My name is James Sutherland, and presenting with me today is Katie Cromali. As you said, I was the team leader for the UMD's graduate team submission to this past year's Vertical Flight Society student design competition titled Leonardo's Aerial Screw 500 Years Later. And as the name implies, this competition was focused on a sketch made by Leonardo da Vinci in one of his many manuscripts and folios. In 1489, Leonardo drew what is often considered the first heavier-than-air rotary wing vehicle. However, this conceptual design has been cast aside to history and deemed ultimately completely ineffective without ever undergoing serious technical analysis or testing. So we were tasked with designing a vehicle that relies on one or more aerial screws to provide lift and thrust for the vehicle. Where an aerial screw is defined as a single blade with a continuous surface and a solidity equal to or greater than 1. And while previous years of design have focused on extreme mission profiles, the main challenge for this design is to prove the feasibility of an aerial screw. And as such, the mission is designed only to demonstrate the vehicle's ability for stable hover and flight. With a 60-kilogram passenger or pilot, the aircraft must take off and hover at least 1 meter off the ground for 5 seconds, then fly at least 20 meters over the course of 1 minute before hovering and landing for a total mission time of 70 seconds. But before looking at the full vehicle, we first need to answer critical questions about the aerial screw. First, can it generate lift? And if it can, why haven't aerial screws flown on a vehicle before? And to start, we first have to define the aerial screw design space. For an aerial screw, you can no longer identify blade pitch, chord length, or even an airfoil profile. And so we instead have the following parameters. We looked at the number of turns in a rotor surface, the pitch, defined in the same way as a physical screw, the dimensional height per turn. We wanted to investigate the effect of a lip, essentially a small winglet-like surface at the tip, as well as the taper, which is the ratio of the starting radius to the final radius, and lastly, the hedral angle, which is the angle the surface makes with respect to the horizontal. And we identified the leading edge as the beginning of the screw surface and the trailing edge as the very bottom. Because of the novel geometry, low-order modeling is an incredible challenge for these aerial screws. So the first step of our investigation was small-scale experimental testing. We came up with 10 designs to isolate each parameter and determine its effect on the aerial screw's performance. These new rotor designs were approximately a 3-inch in radius and were 3D printed out of PLA material and installed on a test stand to measure their thrust, torque, as well as electrical power. This test stand underwent a few iterations and ultimately clamps the shafts at both ends due to the large vibrations that we saw during testing that broke some of the plastic rotor shafts. And it was through this testing that we can hope to know if an aerial screw can truly generate lift. And I'll go through some of the results for each parametric change. First, we investigated the number of turns. Our baseline rotor had a single turn. And in this left plot, we see the dimensional thrust versus RPM, and on the right, the mechanical power. We found that a second turn increases power as we expected to find, but unexpectedly, the second turn actually reduces the total thrust. And so overall, we conclude that more turns degrades the screw efficiency. The next parameter is the screw pitch. In early tests, we discovered that the parameter really is the pitch to radius ratio, here denoted as PR. We have 3 test specimens here, starting from our baseline, one with a lower pitch and one with a higher pitch. However, we found that as we increase the blade pitch, we see a corresponding increase in thrust. But in terms of power, the baseline pitch, the intermediate pitch ratios, had the lowest power based on these results. Next, we studied the effect of a lip at the tip that either points up or down. Our hypothesis was that a downward lip would help push any radial flow that's on the bottom surface downwards and help to generate thrust. However, this proved not to be the case, as the downward lip generated lower thrust than no lip at all. And an upward lip showed little effect on the thrust, while all 3 rotors showed similar power. So we can conclude that a lip is not effective to improving your screw's performance. Leonardo's initial sketch appears to also have a taper on his screw that increases the radius from the top to the bottom. And so we also wanted to be sure to investigate this parameter. We tested 4 rotor designs that looked at screw taper as well as the number of turns. The taper is either increasing from the leading edge to the trailing edge in a ratio of 1 to 2, or decreasing in a ratio from 2 to 1. And we looked at both single and double turn configurations. We discovered that a decreasing taper, the 2 to 1 ratio, actually produces negative thrust, while an increasing radius causes higher thrust over the baseline, which isn't shown here. And here the number of turns does provide a slight benefit to the thrust, but a significant increase in your power. And thanks to an incredible effort from our team, especially Ilya, we were able to generate 417 rotor test points before the labs and campus facilities were closed last March due to COVID. Given more time, we would have loved to investigate these parameters even further with more parametric changes. But based on these results, we found that a higher pitch and a 1 to 2 taper ratio tend to generate more thrust than other designs. And we weren't able to test the hedron angle due to structural failures during testing. Additionally, we found that balancing these screws was going to be a large technical challenge. The large height and lift imbalance generates large 1 per rev moments about the base of the shaft. However, at this point, we are now able to quantify the lift generation of the aerial screw, but we still lack a physical understanding for how it operates. And so we took these results to inform our CFD analysis. The CFD analysis is performed using an in-house CFD code named Hamster. And this study was limited by the challenges in both creating the mesh for these screw geometries, as well as the limited time required for analysis. We selected the highest performing or most interesting geometries from an experimental test and scaled them up to a 1.5 meter radius to be on the same order of scale as expected for the full vehicle design. And this allowed us to visualize the entire flow field and reveal the key to generating lift with an aerial screw. We discovered a vortex that's generated at the leading edge and remains attached along the entire rotor surface, which we now call the Da Vinci vortex. Due to the high pitch and the large taper, this vortex remains attached just above the surface at 80% span along the entire length of the screw. And plotting the pressure along the surface, we see minimal pressure difference between the upper and lower surfaces without these vortex, but in the presence of the vortex, a very large area of negative pressure on the upper surface, and therefore significant lift. And of these 4 geometries, while the taper geometry does have a lower coefficient of thrust than the anhedral and the high pitch configurations, this is actually due to having less than 60% of the surface area of those untapered designs. And so the thrust per rotor area is equivalent. However, the taper design ensures the strength of the Da Vinci vortex is constant over the entire surface, hoping to ensure that the thrust distribution is more even and trying to balance the rotor. So for this reason, we selected the taper design for the rest of the vehicle. And so now we've answered our critical questions for the aerial screw. Yes, it can generate lift, and this is through a vortex that stays attached to the upper surface. But the rotor is inherently imbalanced, which causes major structural concerns that need to be addressed. I'll address our solution to this problem in a later slide, but at this point, we have enough information to start the design of our vehicle. With a physical understanding of how the aerial screw operates, we move forward with the physical design for this vehicle around this unique rotor geometry. The first step is to determine the configuration of our aircraft. We divided our initial concepts into two categories. The first is a rotor configuration, where these concepts were designed to provide sufficient anti-torque for the vehicle. We include a single main rotor with a tail rotor for anti-torque, because the RFP did allow for non-aerial screw designs for vehicle control. But other methods includes a tip jet or coaxial, a multi-rotor, and tandem rotor designs. The second control category is concepts for controlling the vehicle in flight. For the aerial screw, cyclic or collective controls are not possible because changing the pitch requires a change in surface area, which would tear or buckle the surface. And so we had to come up with some novel strategies to control this vehicle. One option is to gimbal the entire rotor shaft to vector eco thrust, or placing aerial screw propulsors along the body. If there is a tail rotor, we could implement cyclic pitch for full control, or lastly, a trailing edge flap could potentially vary these rotor forces. However, the effectiveness is unknown, especially considering the unique lifting mechanism of this screw. And so based on our design drivers, we selected a quad rotor configuration that provided the highest maneuverability through RPM control, a simple anti-torque solution through balanced rotors, and a durable and robust platform to design. Our vehicle, Helico, has a gross takeoff weight of 609 pounds, and so it's a relatively light vehicle, but the aerial screws make it very large. These screws start at a 2.4-foot radius, but taper out to 4.8 feet at the bottom of the rotor, and has an overall height of almost 11 feet and a large footprint of over 400 square feet. The name Helico is derived from the Italian root word for helix, helicopter, and propeller, just as the aerial screw is the root inspiration for all modern helicopters. And here are a few special features of Helico, as well as an overview for the remainder of this presentation. The modernized aerial screw is designed to generate lifts through a vortex attached to the upper surface, and a small tip mass extends out from the shaft to essentially cancel all 1 per rev moments. While we're able to generate thrust, every ounce is critical, and so the triangular configuration of cellular trusses in the support arms minimizes the structural weight. The rotors are powered by an all-electric power plant for efficient power distribution and rapid RPM control. And lastly, Helico is equipped to complete this flight completely autonomously based on waypoint navigation. The final rotor design consists of a single turn with a pitch of 6.3 feet and maximum radius of 4.8 feet in a 1:2 taper ratio. In hover, each screw rotates at 367 RPM and generates 152 pounds of thrust while consuming 67 horsepower. And part of our design philosophy was to root this design as much as possible in Leonardo's first concept. So our aerial screw evolved directly from his sketch to a useful rotor with minimal design changes. First, it's reduced to a single turn to reduce the load imbalance due to the CG offset. Next, we increase the pitch to give the screw higher angles of attack and increase its lifting capabilities. Then, an aggressive 1:2 taper keeps the vortex, which is generated at the leading edge, attached over the full screw length. And lastly, the wood and canvas materials from Leonardo's design are upgraded to lightweight aluminum and performance sailcloth. Where these modern materials reduce the rotor's structural weight and help make the aerial screw more effective. The rotor is centered around an aluminum shaft, where titanium brackets hold 5 carbon fiber spars. And these spars are each individually sized due to the unique loading conditions based on CFD air loads. For additional support and to help maintain the screw shape, 2 helical carbon fiber ribs are placed at 75% span and at the tip. And this skeleton structure is wrapped in a high-performance Dacron sailcloth material to give the aerial screw one continuous lifting surface. The final challenge for the rotor design is keeping a single-bladed rotor well balanced. The aerodynamic forces are not distributed symmetrically over the surface. Additionally, even if the CG is located over the shaft, there's a centrifugal moment generated due to the rotor height. A combination of these forces ultimately snapped the few shafts of tested rotors and would prohibit Helico from flying if not addressed. After many design concepts, we found that adding an additional tip mass to create a centrifugal moment equal and opposite to the 1 per rev imbalance would help eliminate these net moments. The placement of this quarter-pound weight is only possible thanks to the high fidelity CFD air loads and leads to essentially no net moment over the entire range of operating RPMs required for control. Moving down from the rotors, we reach the nacelle. The rotor is attached through a thrust bearing, lift struts, and flexible coupling to the powertrain. This powertrain is powered by energy-dense, high C-rate lithium-ion batteries that are located at the bottom of the cell, with a motor controller for the MRX 188 electric motor. These electric motors allow for rapid changes in RPM control and are crucial to providing the adequate control in flight. Each nacelle contains an individual power plant for each rotor in order to provide the extra weight of running the high voltage and current power cables along each arm. The electric motor lies in line with the two-stage gearbox and transmits power up to the rotor. This gearbox is a two-stage double inline planetary gear arrangement and reduces the motor's 4,000 RPM down to the rotor's 376 RPM, with a comparable step up in torque. And because the motor shaft is directly in line with the rotor shaft, there's no need for any bevel or helical gears in our transmission. To support each rotor in a nacelle, the support arms are made of a triangular configuration of trusses built from individual toes of carbon fiber. This truss provides incredible strength to weight ratios and is placed in a triangular configuration to increase the bending moment of inertia. And while these arms extend 6.3 feet in length, they weigh only 15 pounds. Due to the long strands in each cell, our detailed finite element model indicates that it's more likely to fail in buckling under a bending load, but maintains a factor of safety of 1.5. And because of the large forces and vibrations caused by the rotors, the first bending frequency of these arms is designed to be 2.5 per rev in order to avoid any resonance. And at the root of these arms, they're each attached to a central truss from which the pilot seat hangs below. And the pilot is not a true pilot in the same way. Once Helico has its planned path, he really becomes a passenger and can enjoy the ride. But the pilot sits in a fully transparent cockpit and is protected from the rotor downwash. The touchscreen multifunction display allows for waypoint entry prior to flight, and then during flight provides system monitoring. The pilot has a full range of view that can be augmented with external cameras for a full 360-degree vision. In addition to those cameras, Helico has a full suite of avionics hardware. There are optical flow sensors and cameras placed around the airframe to help Helico avoid obstacles and identify safe landing areas. The flight computer, GPS, and radios are housed above the pilot. In each nacelle, there are LiDAR sensors to get elevation data and detect ground obstacles, and then IMU to monitor vibrations and deflections in each nacelle. That covers the physical components of Helico's design. I'll pass the slides off to Katie to discuss the stability analysis of Helico in hover.
Thanks, James. So we participated in the bonus task and used ART's Flight Lab simulation software to look at Helico's stability. First, we built a model to match Helico geometrically. This model consisted of 36 blades that are identical in taper and twist, but have different radii and therefore different masses. This model is pictured below in the center. As you can see, it is a pretty good visual match to Helico, but took a lot of computation time. And since Helico has 4 rotors, we made a simplified model with a reduced number of blades, seen in the bottom right. We discovered while looking at the CFD results that Helico's acting lifting mechanism is a vortex. Flight Lab uses airfoil tables in the simulation, but this vortex cannot be adequately captured simply using an airfoil table. So we changed the model's geometry by changing the twist of those spanwise sections of the blade where this vortex occurs, so that we can get a more accurate lift distribution for the model, while still reading from an airfoil table. This changes the model's geometry, but provides a better aerodynamic model. The model also features a tip mass counterbalance in accordance with Helico's design that you can see in the bottom right. This was confirmed in Flight Lab to reduce head moments by 96%. We compared our simplified Flight Lab model with CFD results generated for Helico. Shown here are the power and thrust versus tip Mach number. The results carry the same speed and are within 20% of each other at Helico's nominal speed, which is denoted with the red line. We felt confident that the Flight Lab model was accurate enough to look at Helico's stability in hover and how it responds to a wind gust. The eigenvalues of the full vehicle were found to be stable, giving us a stable system in hover. We then looked at how the isolated rotor responds to a horizontal 30 foot per second wind gust. It is important to note that Ellico's forward flight speed is just 1 foot per second. So this wind gust is 30 times larger than Ellico's forward flight speed. Ellico's isolated rotor gust response was compared to an equivalent conventional rotor to give us a baseline for this response. The equivalent rotor was a 4-bladed rotor that gave the same thrust as Ellico's isolated rotor in trim. And its gust response can be seen in red in the bottom plot. The mean hub loads differ by only about 20% or 20 pounds. The main difference in the responses are the oscillations about the mean hub loads. Ellico's isolated rotor has high amplitude 1 per rev vibrations, while the conventional rotor has low amplitude 4 per rev vibrations. These high amplitude 1 per rev vibrations are due to the model's dissimilar blades encountering the gust, whereas the conventional rotor has identical blades. In conclusion, we found that we could reasonably model Ellico in Flight Lab, both geometrically and aerodynamically. We calibrated the model with high fidelity CFD results to ensure its accuracy, and we found that Ellico is stable in hover, and Ellico's isolated rotor has a stable response to a gust 30 times its forward flight speed. Thank you.
So now knowing that our vehicle is stable in hover, we can look towards implementing a standard flight controller with an inner loop for attitude control and outer loop for position control. And these graphs show how closely Ellico follows the planned flight path using this controller. During the process of design, safety was always a primary concern. And while the mission only requires flight 1 meter above the ground, if Ellico is at higher ground elevations and encounters an emergency, the electric motors can be driven to a 0 torque state and enable an autorotative index of 27, which is higher than the Bell 222 and AH-1 helicopters. In the event of a closer to ground emergency, the monopod legs under each nacelle are designed to absorb a 4G hard landing or 1G side load. And this figure here shows one of the multiple design iterations went through to ensure this result. Lastly, the low disc loading of 2 pounds per foot squared allows for a low downwash to ensure safety of the pilot and ground crew. As designed, Ellico has enough excess power and energy to enable rapid climb rates and hover at altitudes well exceeding mission requirements. In addition to this, the quad rotor configuration combined with this excess power allows for very large CG offsets. This graph on the left shows the rotor power given to the front and the back rotors as the CG shifts forward. And so with 0 shift, we see the front and back rotors show the same power requirements. But as the CG shifts forward, the front rotors require a higher power in order to accommodate this higher load, and the back rotors are offloaded. We find that 1 full rotor radius of CG offset is the power limit for the front rotors. And so if the pilot seat is replaced with some cargo, Ellico can accommodate large imbalances. And if we assume Ellico flies at the minimum required flight speed of 1 foot per second, Ellico boasts a ferry range of 74 meters per second with the mission payload. And this already well exceeds the mission requirement. But as we trade off payload for battery weight, this range can be extended to 311 meters. And if Ellico is required to fly it for minutes and meters, but instead hours and miles, then we could swap out for a turboelectric generator to replace the batteries as a power source. The electric motors are required to provide the rapid RPM control and reduce vibrations, so a pure turboshaft design can't be used. Ellico was sized for a total of 3 minutes in hover, but we found that for missions exceeding 5 minutes, the turboelectric generator provides a lighter design. And with the desire to potentially build this vehicle to further study Leonardo's aerial screw, a low-level component-based cost estimate was performed. And this analysis is based on estimates for individual part machining and labor costs based on the fabrication graduate students have done for similar structures at UMD. In all, the fabrication cost is estimated to be about $200,000. In its current design, Ellico is best suited as an educational demonstrator or interactional exhibit at a museum. With its expanded payload capability and endurance, Helico enables anyone the opportunity to experience flight as Leonardo da Vinci envisioned it 500 years ago. In summary, Helico is a highly capable quadrotor vehicle that takes advantage of a vortex attached to the aerial screw surface to generate lift. The 1 per rev moment imbalance is solved by a small tip mass attached to the rotor shaft, and the quadrotor configuration and all-electric design provide superior control in flight. The ultralit structure and components minimize the structural weight, and the flight control and avionics hardware ensures stable and autonomous operation. All in all, Helico utilizes modern technology and analysis to bring Leonardo's dream into the modern age. I want to take a moment to thank our University of Maryland faculty, as well as our fellow grad students, who without them, none of this would have been possible. And I thank you for your attention. That concludes the presentation, and we'll be happy to take any questions.
Thank you, James and Katie, for that excellent presentation. We do have one question that came in while you were presenting from Delaney Jordan. How do you determine your intricate truss cross section?
So that cross section was designed based on some previous results that have been looking at this design for bicycle airframes and other applications, and we adapted it for our larger scale design.
Okay. Eric Sachs commends you on your excellent presentation. The Da Vinci vortex revealed in the CFD analysis is very interesting. Is wind tunnel testing planned to investigate this phenomenon further?
I know that currently we have at least one student who's working on making a smaller scale model for this aerial screw. One of the challenges is the rotor imbalance, but we definitely want to continue to investigate this effect and try to validate and compare both experimental and CFD results.
Sky Sartorius asks, did you look at alternative leading edge shapes to affect the Da Vinci vortex?
The leading edge shape was not something that we investigated strongly. We stuck with just a rounded leading edge just to avoid any blunt body. But beyond that, no.
Okay. Delaney Jordan again asks, what was your vehicle weight? How did you compute it? How did you verify you had enough lift?
The vehicle weight was 600 pounds, 276 kilograms. It was computed based on group-based sizing code. So varying the disc loading based off of the experimental results. We verified we had enough lift based on our experimental results and scaling those up in conjunction with those CFD results. They showed good agreement, and we were confident with our understanding for how much lift we could generate.
Okay. Just refresh it here for a second. Looks like that answers answers all the questions that were put in the chat. So again, congratulations on your winning design, and good luck with your grad student studies. And to everyone that joined us here in the aircraft design sessions the last Monday and again today, we appreciate your attendance at the forum, and look forward to hopefully next year being able to gather in person and chat more about some of these interesting things that we're seeing in aircraft design. Again, thank you, and best wishes.